Okay. So good morning and good afternoon, everyone, and welcome. I am Lisa Biasetto, Associate Professor at the University of Padova, and it is a pleasure to introduce today's webinars, which explore one of the most critical and often underestimated aspects of advanced ceramics manufacturing, the science of colloidal processing and rheology. Ceramics are increasingly expected to perform in demanding environments, from structural and energy application to electronics and additive manufacturing. Yet the performance of ceramic component is not determined only during sintering or densification. In many cases, it is decided much earlier at the level of suspension formulation, particle interaction, and flow behavior. Understanding how particles behave in liquid media, how they organize, and how they respond during shaping processes is fundamental for achieving reliability, reproducibility, and scalability. So for today, our first webinar is titled Understanding and Controlling Ceramic Processing through Rheology, and will focus on how rheology serves as a powerful tool for predicting and controlling material behavior during processing. Our speaker is Professor Marcello Romagnoli, full professor at the University of Modena and Reggio Emilia, Italy. And I will introduce later the second webinar from Professor Simge that will speak later. So I will give the stage to Marcello.
Okay, good afternoon, everyone. My name is Marcello Romagnoli, and as Lisa has said, I work at the University of Modena and Reggio Emilia in Italy. My university is close to one of the most important ceramic tile manufacturing pole. Since my student day, I have also worked in ceramic manufacturing companies as a worker. As a university researcher, I have immediately focused on rheology applied to ceramic and geopolymers that are a special type of cement in such a way. I have collaborated with companies producing chemical additives, developing a formulation using innovative approach, as for example, design of experiment or neural network, that is the base of the very famous today artificial intelligence in more than 20 years ago. And well, today I'm the director of the Hydrogen Research Center of my university. This may seem like a very different field from my initial focus, but in reality, when I started working there over 20 years ago, I transferred much of my knowledge developed in the ceramic production, especially in rheology, in the field of the hydrogen. In every case, we have some parts, some technology of hydrogen that are made in advanced ceramic, for example. Today, I'd like to take you into a world of the rheology, but we'll do so from a very practical perspective, how it helps us to understand, and most importantly for me and for, I imagine, for you, control ceramic processes. And we all know in our industry, if you can't control the flow, you can't control the quality of the final products. So I start to share my screen. Okay. I think that this is the right way. Yes.
Yes. Yes.
Okay. Start. What is rheology? Formally, it's a science of how matter deforms and flow under stress. But in our daily work at the plant or in the laboratory, it's much more than a simple definition, because it is really a tool that allows us to quantify how a material responds to an external force, be it a liquid, a solid, or better, a viscoelastic material. Whether we are talking about simple Newtonian fluids like water or also complex shear thinning pastes, rheology gives us the mathematical relationship between the stress we apply and the deformation we get. This is a secret sauce for designing stable processes like extrusion, pumping of slurry, wet grinding, glazing, tape casting, slip casting, and so on. So rheometry is the part of the rheology science, and that deals with how to make the measurement necessary to develop models. While rheology tells us why a material flow, rheometry defines the experimental procedure that in rheology are very, very important, because if we change the procedure to measure the rheological behavior, we can change also the response of the material. So the rheometry is really important and is the other side of the coin with respect to the rheology. Important for the rheology that if we introduce good data, good result, we can obtain also good output. But vice versa, if we introduce garbage, we obtain garbage. So for this reason, the rheometry is really an important part of the rheology. So in this slide, in this map, I want just show you how broad is the field of the rheology. When we talk about ceramic processing, every stage depends on several variables. We have steady shear rheology when a suspension travels, for example, in a pipeline, but also a transient rheology for phenomena like thixotropy, when a material flow when agitated and solidify when let to settle. And let's not forget the linear viscosity or linear viscoelasticity. It's our best method for studying the microstructure of a material without destroying it. When I flow the material, I also change the microstructure. But if I use the linear viscoelasticity approach, I don't change the structure of the material. This structured approach is what transforms ceramic production from an art to a predictable science. Fortunately, we have many tools, many instruments, not only instruments, but also instrument for our brain to know how to use, some of which are demonstrated in this slide here in this part. The rheological models are also very important if we want make a simulation using software like CFD. And in this case, if we want a dialogue with the software, we need of mathematical models. We use springs, for example, for spring like this one, for the elasticity or dampers like this one, for the viscosity part of the behavior to build the constitutive equation. If you look at the curve here, we can see a behavior of a material that deform over time we have an initial elastic jump like this one, then a gradual creep, and finally some deformation that we can never get back, like this one, for example. These models are essential for predicting how a past will behave in an extruder, for example, or in a 3D printer layer production in the additive manufacturing, which support the weight of the next one. So we have several rheological models when the material flow, for example, the Newtonian one that is the most simpler and is great for water or slip of suspension with a low amount of solid content, but not for the one that in general use in ceramic production, both in traditional and in advanced one. If we use the Bingham model, a bit more complex, we introduce the yield stress concept here. And if we use the power law, this model is perfect. It's very good for shear thinning slurries, but probably the most used is the Herschel-Buckley model that introduce both the yield stress, but also a non-linear flow. But we have also other model, and we can decide what it is better for our experimental data. Here are the variables that affect the rheology of a suspension. You can see the chemical effects and physical structure, the shear rate, the time, the temperature, and the pressure. For example, if we have Newtonian fluids, so we talk here about the chemical and physical structure. Especially the chemical and physical can determine a Newtonian behavior or a non-Newtonian behavior. In the first case, this one, in this diagram, shear stress versus shear rate, or is a horizontal line in the graph viscosity versus shear rate. We have a constant viscosity. That means that we double the force, we double also the speed. Different is for non-Newtonian fluids, where we can see a decrease of the viscosity with the increase of the shear rate, but also an increase of viscosity again with an increase of the shear rate. And this is very dangerous if we must pump a slurry in a pipeline, for example. So know what kind of behavior we have in our fluids is fundamental also in the process. Important is also the role of the solid loading. In ceramic, we are always fighting the solid factor, the solid fraction. In many cases, we want a high solid loading to reduce, for example, the shrinkage, and or also increase the density of the body in the green body, or also the body after the firing. But look at what's happened at the viscosity. At the low concentration, for example, here, we have a behavior that almost linear. But as we approach the maximum packing limits that depend by several factors, it's not a constant value, and it's not constant for all the ceramic system. The particles start corroding each other, the friction and mechanical constraint take over, and the viscosity diverge sharply and increase a lot. This is why, for example, chemical dispenser and particle size distribution are so critical, and we need to use them if we want to have a high solid content. Not only the amount of solid content, but also the shape of the particles is important, and is important almost as much as the size, even if the size usually dominates. From this graph, shape versus viscosity, here you can see that these particles with the shape of rods increase the viscosity a lot with respect to, for example, the sphere, and can determine also the behavior of the system in shear condition. For example, we can have a shear thinning or a shear thickening. For example, if you have rods, it's quite simple to have shear thickening behavior at high shear rate, because they have an orientation along the flow, and this reduce the viscosity of the suspension. They determined also the packing density and also the surface area that is low when we have a sphere shape, and increase with the increasing of the different shape with respect to the sphere. Particle size distribution is another important, yet often underestimated the method for controlling the viscosity. In general, broader and more optimized distribution, as for example bimodal or polydisperse distribution, allow smaller particles to fill the space between large ones. High packing density, greater free water lubricating the flow, low, and this permitted to obtain lower viscosity. This is quite simple, but if the distribution become too narrow, the particles can packing tightly together. We have less free water, and so obtain higher viscosity. You can see here, for example, that the lower relative viscosity is not with the small particle or large particle, but somewhere just in the middle with size distribution that contain both the particles. Just to obtain a better viscosity, but also a higher density, the researchers have developed several models. These are just two of the most used, the Andreasen and the Franken-Dinger model. They work, from my point of view, very well if the particle, the real particle, are similar to sphere, but they don't work so well if the particles are not spherical. In this case, in my experience, approach like design of experiment are better because they consider also the shape of the real shape of the particle. The data potential is another important parameter that affect the chemistry, that depend by the chemistry of the suspension. You know that the data potential is the potential of the slipping plate, and if its value is high, in absolute value, we have particles that are very dispersed, and so this produce a lower density and vice versa. We can work on this parameter, for example, obtaining an electrostatic stabilization, increase, for example, the potential. We can work with polymers, for example, to stabilize the suspension by steric stabilization, or also electrostatic stabilization that combine both electrostatic and the steric stabilization. And also in this case, we can obtain stable suspension. We can design the rheological behavior of the suspension, just considering the kind of process that we have. Attention, because we have said Newtonian, non-Newtonian, and so on, but the behaviors depend also by the shear rate. We can see at, for example, low shear rate, a quasi-Newtonian behavior, like in this part. After it's become non-Newtonian, but at very high shear rate, it's become shear thickening, and so if not always the suspension maintain the same behavior at all the shear rate. This is another important aspect. Effect of temperature. We know that the temperature strongly affects the viscosity, both in the slurries, but also in the case of the glazes during the firing. And we know that the relationship is exponential, like this one. So when increase the temperature, decrease very fast also the viscosity of the glaze or the suspension. But also if we work at low temperature, close to the room temperature, we must consider also that the temperature increase the kinetic, for example, of dissolution of some salt present in the raw materials, but also increase the degradation of the polymer that we eventually have used as additive. And so we could also see a decrease of the viscosity of the, not the viscosity of the rheological behavior. That means also increase, for example, of viscosity, because we have a solubilization of the salt and the degradation of the polymer additives that we have introduced. So the effect of the temperature is not in one direction, but it can be also in different direction. The pressure, also the pressure can change the viscosity, but we must see very large, very big variation of the pressure just to see evident small variation of the viscosity. But this could be important, for example, in some process, like, for example, injection molding. So we can see here some application, for example, in slip and tape casting. The important parameter that we must consider is the viscosity. We need of a low viscosity with a yield stress, especially for the tape casting, just to maintain the thickness of the tape, but also in the case of the slip casting, for example, when we introduce the slip inside the mold, we need of a very low shear viscosity, but just to have the casting, we need of a high thixotropy of the system. And we can check this parameter using rotational rheometry not just the 4-cup measurement and similar, but the rotational rheometry is the method, the best method to measure all these parameters. Again, for example, in the sprite drying, we need of the right viscosity, apparent viscosity of the materials, not so high just to have problem in the pumping and of the slurry inside the sprite dryer, but not too low, just to obtain not spherical or similar to sphere aggregates that reduce the flowability of the powder. We haven't time to talk about also the rheology of the powder that is different with respect to the rheology of the slurry, but also this kind of rheology is really important today, especially in the production of big, large tiles that require to put the powders in a homogeneous way in a large area. And also in this case, we can use rotational rheometry. Other application, gel casting, here it's important not the linear viscoelasticity, and in particular to measure parameter like G prime, G double prime, that give us some information about the kinetics of gelation of the material, and also to understand the structure of the material. In this case, we must use the oscillatory rheology and with small amplitude oscillatory shear test. Traditional extrusion, here is important to measure the yield stress and also the wall slip and have a behavior that is shear thinning, but with a yield stress that permit to maintain the shape after the extrusion, like in this case. Here it's possible to use capillary rheometry and high torque rotational rheometry. Robocasting is another interesting method that grow in this year. Here we need a minimal stress yield, a high G prime at rest, just to maintain the shape, and a very fast structural recovery. So also in this case, a good thixotropy. Also in this case, we must use oscillatory rheology and creep and recovery methods. This is another similar method that is an additive manufacturing that can be used. Also in this case, we can use a model like the Bingham, Herschel, Buckley, because we need of a high value of yield stress, but also an high thixotropy. And finally, if you want to study, for example, geopolymer concrete, the rheology is similar to the rheology that we use for the cement, for example, but we can use also the oscillatory rheology just to study the kinetics of the reaction that we have in geopolymer during the increase of the mechanical strength, the mechanical characteristic of the geopolymer. So in this very quick talk, I hope to have explained, convinced you how much is important is to understand the rheological behavior of the system that we use, and also finally is necessary to have a high sensibility, a high rheological sensibility, because it's very easy to make the bad conclusion from rheological test, because the rheology is not only just a measure that give a number, but it's necessary to understand well the theory that is under this measurement and this model.
Thank you, Marcello. Very nice webinar, very interesting. I guess maybe we have time just for one question, if any. Just by my side, can you hear me?
Yeah.
Okay. You showed a ratio talking about the particles effect.
The particle size distribution?
Yes,
Okay.
here, yes, 14, number 14.
14?
Yes. So the CPFT is a kind of shape factor.
No, it's the cumulative percentage, is the amount of material that is up to the value D, for example. For example, the 50% of the materials has for example, a size distribution that is lower than the value.
D value. Okay. Thank you.
Is a way to describe the particle size distribution curve.
Okay, thank you. I see a question in the effect of T slide. You equated constant A and B with activation energy and R. What
Yes.
is R? Oh, okay.
Yes, R is the here. Here. No. Is the classical gas constant.
Yes. Okay, unfortunately, we have to move to the second webinar, otherwise we will steal time to Simge. So thanks again to Professor Romagnoli for the very interesting webinar. And I will move to the second webinar. The title is Colloidal Processing of Ceramics, Highly Loaded Suspension from Particles to Properties. And this webinar takes us deeper into the interconnected nature of ceramic processing. Rather than viewing each processing step independently, this lecture highlights how choices made at the particle level propagate throughout the entire manufacturing chain. So we have the honor to host the Associate Professor Simge Aygün, that is Associate Professor from Middle East Technical University in Turkey. So the stage is yours.
Thank you so much for the introduction, Lisa, and thanks for the invitation. I'm really happy to be here for this webinar. So I'll just share my slides first. Can you just confirm? Can you see my slide? Okay, perfect.
Yes.
So yeah, I'm going to talk about the colloidal processing of ceramics, but first I want to talk a little bit about myself and what I'm working on. So I have very broad background from chemical engineering to material science and mechanical engineering, but they all rooted in colloid and interface science. So I currently have like few projects. One of them is bismuth tin-based liquid metal particles and their derivatives, and also additive manufacturing of ceramics. And I do have a lot of like collaborative work, particularly in ink formulation development. And in that area, I work with like metals, polymers, ceramics, composites, everything. So, okay, I cannot move. Yep. Okay. So here you can see a very basic schematic of colloidal processing of ceramics. We start from particles, we mix them with solvent to obtain those suspensions, and Marcello make it quite obvious that the suspension properties and quite critical for the end products. And then here, once we obtain that homogeneous dispersion of the particles, we shape those suspensions, we dry them and sinter them depending on the application. And here, that homogeneous dispersion is directly related to surface chemistry, interparticle interactions, and we need to optimize the rheology, and solid loading is function of solid loading affects all the others. And here we really need to have like homogeneous dispersion of those particles, because otherwise we start to see defects in packing, and that leads to inhomogeneities in sintering, and then the properties in the end product will scattered. So this is a long path, but I do really believe that like at every single step, we need to understand and optimize the process. And obviously today I'm going to focus more on that colloidal processing part. So if we are going to develop a recipe, it's a little bit harder than it looks, because like the demands are growing. We need to generate like complex geometries. We are looking for better functionalities or multifunctionalities, and we need like scalable processes. Even though that field advances, the formulations that we develop is largely empirical. And if someone is going to develop a recipe, what we do is we just look at the literature and try to see like similar systems. There are hundreds of studies. It's difficult to find that perfect match, but sometimes even in the same lab, with the same formulation, we are having difficulty to reproduce those results. And the other thing that we can do, we can just like screen the dispersants that we can use and see what works to solve one of the problems. But then during that processing steps, we face with another problem, and then we are using another additive. And with each problem, we are adding new additive that introduce new introduction, and the complexity grows. Those recipes becomes quite delicate. So sometimes even just changing the batch of powder leads to failure in the process. So my suggestion in that case is just to back to fundamentals. So I guess this is a very good example, even though it's not from ceramic field. Here, what you are seeing is a suspension formed from catch black, which is conductive carbon, in an aqueous electrolyte. And the only difference between those two images is the adding sequence of the powder. So in the left-hand side, we have electrolyte, salty water, and then we add catch black into it, and we see obvious phase separation. And on the right-hand side, we put the catch black into water, and then we add salts into that, and we have that homogeneous dispersion. Identical chemistry, but the results are completely different. So if you look at that in detail, once we add that catch black in electrolyte, we see that phase separation. We can increase the homogeneity by applying ultrasonication, but after just 2 hours, we observe that phase separation. However, in the other case, we add catch black into water. We actually allow that electric double layer to form, and then we add salt into it. Then we obtain a stable suspension. So sometimes we are just overlooking, and we may not write how we really form those suspensions. Like the adding sequence is quite a simple thing to skip during those like paper writing, but even that is critical in formulation development. So what I think is that we really first need to understand the particles, their physical and electrochemical and chemical properties, and then we need to determine the target solid loading, so we would know how much interparticular space that we have and how much we can control the interparticle interactions, and only then we can generate simple recipes that are reproducible and scalable. So with this approach, today I'm gonna share some of my own research from my lab, and I will use them as a case study and try to highlight the parts that I find important or interesting. So we first start with the particles, right? So the dispersion quality is the particle properties are extremely important in dispersion quality. And here what you are seeing is like zeolite powders. In this, let me laser, okay. So in this image, we have synthesized powders, and you realize that between those powders, there are like nets. And if you are using the zeolites in lab environment for catalysis or for gas absorption, that is totally okay because the important part is the porosities or the available surface area. However, if you are going to scale up that process, you need to give shape to those zeolites. So for those shaping procedures, we commonly employ colloidal processing, so we need to make suspensions out of them. So if you add those particles into suspension, they are not going to act as primary particles, but those aggregates will flow around. So depending on the density difference between the solvent and those aggregates, they're either going to cream or sediment, but it is difficult to homogeneously disperse them. And adding just additives, chemicals into that will not break those aggregates. So we need to physically break them. But while doing that, we also need to preserve the zeolite properties. We shouldn't give harm to that porous structure. So what we have done is we employ ultrasonication or ball milling, and those particles were soft enough. So just few minutes of ultrasonication or simple ball milling was enough to break those aggregates, and we could start working with those pre-treated powders later on. In another example, I will give the alumina example. So here we use alumina powders. If you look at the SEM images here, we have like very nice primary particles here, but we also see some aggregates. And alumina is much harder compared to zeolites. So we need to either break them or somehow we need to eliminate those aggregates. So if you look at that particle size distribution, you realize that we have significant amount of those aggregates. And we employ ball milling, like plenary ball milling with zircon balls. It didn't help. We couldn't break those aggregates. And then what we have done, we just sieve those particles. We find that the sieve works just fine. So what we have done, we collect the sieved powders and labeled as undersize, and you realize that we eliminate all of those large aggregates in that sample. And then whatever remains collected on top of that sieve, we labeled as oversized, and as received is the as received powder we have. And then we compare the rheological behavior of those suspensions. So what you see here is that the undersized particles, the smaller particles, exhibit much lower viscosity. So what we know is that if the particle size reduces, then the viscosity increases. However, here we have aggregates, so they cannot flow or rotate in that suspension, I guess. So they exhibit as like much higher viscosities compared to those smaller ones. Once we use those particles and form suspensions with the same additives and binders, and they all prepared at the same way. The only difference is the agglomeration state of those particles. So with the oversized particles, we could obtain some shapes, but with SEM, you can see like very large heterogeneities in their surfaces. With as received powder, it looks nice, but still you can recognize those some agglomerates. With undersized powders, even at higher magnifications, we couldn't see any obvious aggregates. Besides, since we solved that clogging issue, we could actually print much thinner layers, so we could reduce this surface roughness. Once we sinter those green bodies, the oversized one, it couldn't retain its shape. With as received one, it looks quite nice, but then once you look at in detail, you realize we have some heterogeneities. However, the undersized ones, they look much, much nicer than the others without any obvious heterogeneity. So from here, I will move to lithium iron phosphate, which is a cathode material. Here, you are seeing the SEM image of the commercial nano-sized LFP powder, and they're carbon coated. Yes, their surface area measurements indicate that they are nanopowders, but what we realize is that we have those very large aggregates. And they're carbon coated, so we cannot ball mill them, because if we do so, then we break this carbon coating. And they are to me, too expensive to sieve. So what we have done, we couldn't use them. We just used them as a reference sample, and we synthesize lithium iron phosphate particles, individual particles, and then we develop a technique to individually coat them with the carbons, and then we develop new recipes using those individual powders. So here what you see is that if you load 28% LFP particle here, the agglomerated one, if you use the agglomerated particles, it was like solid, it didn't flow. However, with the dispersed ones, same loading, it flows like water. So since we have quite low viscosity here, we were able to add more and more particle into it. So for here, the K represents the viscosity. We already talk about those rheology models. So this is the power law, the K for the viscosity. So you realize that, okay, so let's say the 48% loading of dispersed particle has relatively similar viscosity with the 25% of the agglomerated one. So that means that for the same volume, I can add more electroactive particle into that suspension that will eventually increase the volumetric energy density. So that if you have an electrical car, that will translate into that if you have the same size battery, you can double your mileage, almost double your mileage. So I hope that I convince you that we need to have those. Non-aggregated particles. Now they are ready to de-agglomerate them. So we still need to work with the recipes. So what happens once we put those particles in a solvent? So here we are back in that zeolite case. What you see here is that we have 70% water, 30% ethanol in that mixture. So for that process, we need to replace that water with the organic solvent. But what happened is that once you increase that ethanol amount, the stability, we lost the stability, even though we use those pretreated particles. So what happens here is that, as you know, once we add those particles in solvent, the electrical double layer forms around them. However, the ethanol has much lower dielectric constant compared to water. So that electrical double layer shrinks and we lose the zeta potential. So if you put those values in the LVO theory, that repulsive energy barrier is reduced. So the electrostatic stability that we have in that suspension is lost once we increase the ethanol amount. So in that case, we cannot use the electrostatic stabilization, but we should look for the other kind of stabilization technique, like Marcello mentioned, like steric or electrosteric stabilization. Okay, this is the organic solvent, but most of the time we use water as a solvent in ceramic processing. So that is from my PhD work, actually. Back then, my aim was to understand why the viscosity of the nanopowder suspensions are unexpectedly high. So we expect that if we have smaller particles, then there's going to be this crowdedness effect, and the particle will interact with each other more. However, even though we include all of those effects, we couldn't still estimate the viscosities correctly. So my PhD work was to understand this, and I was lucky enough to have a very nice PhD student before me. They realized that the melting behavior of water is changing once we add particles, once we add oxide particles. So these are my results, just differential scanning calorimetry analysis of that water. So if you have pure water, you expect this will melt around like 0 degrees Celsius, and we have pure material, just single phase melting event. If you add submicron sized particles into that, we start to realize that there is this shoulder appears on the left-hand side. And if you switch to nano-sized particles, we observe two different melting events. We only have alumina and water, and we do not expect any thermal event from alumina at that temperature range. So that was water. So, however, we didn't know like why this is happening. So we just call it as bound water. Then after a couple of years, we actually had a chance to look at those particles in water under electron beam. So normally electron microscopy, and this technique is called fluid cell STEM. So you know that TEM works under vacuum, so we cannot analyze the suspensions. However, here we used silicon nitrate membranes. They were electron transparent. So once you sandwich that suspension in that between those two windows, you can analyze that sample in vacuum. So what we realize is that there is this cloud around the particles, and we know that this cell is full with water, so the remaining is water, but we realize that there is this different contrast here. And then if you look at if you run chemical analysis, if you run eels here, we find out that this water is actually structured water. And that was quite important to us, because if you think about it, like if you prepare 20 volume percent suspension, then you add 20 volume percent of particle and 80 volume percent of water, right? But some part of that water is not act as a solvent anymore. It is associated with powder, and the powders that you put, they act as like much larger particles. So once we add all of those numbers into equations, we realize that this 20 volume percent loaded suspension behaves like a 45 volume percent loaded suspensions in terms of viscosity. However, if you sinter them, or if you try to shape them, there's going to be a lot of volume change. So that's why it was quite difficult to work with nanopowders at site solid loadings. And that like bound water was quite cool, but we were just working with alumina. So what we have done is we look for the other oxides. Here we have alumina, titania, zirconia, and yttrium stabilized zirconia, the TEM images of the powders that we use, and they all have the same surface area, but they all exhibit like very same free water peak, but the bound water peaks that you see here, it was material specific. Both the melting temperature and the amount of water bound on those samples were different. So we conclude that this is a material specific property. And then I also mentioned that we are working with liquid metal derived bismuth tin particles. Those particles, they are metal at the core, but they form very thin, few nanometer thick protective oxide layer around them. And if you have bismuth tin as a core, that oxide layer is tin monoxide. And what we found is that this very thin oxide layer also formed that bound water. And we confirmed that results with the NMR studies and show that we have a restricted motion of the water molecules on the surface once we have that aqueous suspension. And then we correlate them with optical properties. We also have preliminary results for like LFP or iron oxide. They have like very distinct bound water peaks, and the properties are changing accordingly. But I will go back to that colloidal processing part. So we have non-aggregated particles. We put them in liquid media. Now we need to develop recipes. So we need to use dispersants. So we have that hydration layer, and we have electrical double layer around it. These are a lot. So we know that if we add fructose, that replace that hydration layer, so it frees some of that bound water. And for electric double layer, we can use simple salts to shrink that layer. So what we observe is that just adding that fructose and sodium chloride together could reduce the viscosity 97%. And the green bodies that this obtained from those suspensions were pore-free, they exhibit much higher structural integrity compared to other samples. So then I start to think about this like highly loaded suspensions. If we have nanopowders, we have this carbonless effect. However, if we are going to calculate the interparticular spacing, we assume that those particles, they're like hard spheres. So the distance between them, we do not account for those layers, but we only think those individual hard sphere particles. So if we calculate the interparticular separation distance with respect to the solid loading with those nanopowders, I realized that this distance decreased down to 13 nanometer. But we have this bound water. We also have this electric double layer. Once we add those layer thicknesses into those equations, those values, they become negative values. Obviously, the separation distance cannot be negative. So what does that mean is that those layers, they overlap. So those particles, if they have those overlapped layers, they cannot freely move in that suspension. There is going to be a significant restriction to flow. So the viscosity is going to be much, much higher. So I have this fructose and sodium chloride, so I can shrink those layers. Once we add those thicknesses, then with 4% fructose and 0.01 molar sodium chloride, we could actually able to get non-zero value, positive values here, but with 40 volume percent, the value was quite close to zero. And here, what you see is the sintered products from those suspensions. With 40 volume percent, it is full with pores. However, for the others, even though they're not the best samples that you can get with this powders, they were at least pore-free. So that makes sense to me because during that slip casting, the particles, they consolidate, right? So if they do not have enough free space, they're just gonna settle down wherever they find, rather than trying to find the most energetically favorable spots for better packing. So here we lose this packing properties. So what we stretch a little bit here, and then we increase the salt concentration. So can we like further shrink that double layer by increasing the salt content? We were able to do that, but still if you look at this theoretical densities for the sintered product, they were about like 70%. So they weren't like high enough. So we still need some repulsive forces between those particles. Just having that space is not enough. So with optimum solid loadings, like 20 volume percent solid loading with the additives, those powders, they were the mixture of delta and theta phases. So with them, we could obtain 96% of theoretical density. Once we add a little bit of alpha seed into that, we could increase the theoretical densities to 99%, which is quite high for nanopowder suspensions with this like simple sintering application. So, okay, so that adding up to now, I only talk about those layers, but we also have interparticle interactions. And if you are working with highly loaded suspensions, and if you have very small size particles, or if you have like very limited interparticular distances, using large molecules and additives is dangerous because you are facing with the you may face with the bridging issues. So those polymers, they may bridge the different particles rather than disperse them. So we thought that for those nanopowders, we need to use like much smaller organics. And once we use ascorbic acid, we could reduce the viscosity of those nanopowder suspensions by 98% with only 1 weight percent addition of additives. And then what we also realize is that that additive works with relatively higher solid loadings as well. And recently, we used the same additive for submicron size particles, and with the solid loadings of 45 volume percent, with only use once we use only 0.7 weight percent ascorbic acid, we could reduce the viscosity like more than 90%. So it is still effective. Okay, if we are using mixed solvents, or if we have organic solvents, then we cannot rely on those aqueous chemistries. So what we need to do, or the better option is generally the steric effect. So for those zeolites, we used polyethylene glycol as a dispersant, and then we had to use PVP as a binder for other purposes. And then with optimum recipe, we could obtain this homogeneously dispersed thin films from that zeolite suspensions. Okay, so if we are working with slip casting, we do not use binders. Most of the time, we do not use binders, and just dispersants are enough. But if we are working with extrusion or direct ink writing, or like much, in those cases, we need to use binders. So here, these are the samples that we produce with direct ink writing of aluminum monoliths. And once we use ascorbic acid dispersant and another binder, we realize that we have like variety of defects. Some of them were like air entrapment that we use all around the sample. And then we also realize that there are some drying defects. So here in that structure, we realize that there is this cavity underneath of that sample, or if you do not have cavity at the bottom side, you have hole on the sides. So we thought that, okay, this has to be related to drying, that water in that suspension trying to find its way out from that monolith. Okay, so we control that drying. This time we eliminate this cavity and hole formation, but this time we faced with inward warpening. And if we do not have that inward warpening, then we realize that there is this interconnected pores in that structure. Okay, if this is a drying effect, we thought that if we have much finer features, if we allow that water to go through like the side walls, if we have more porous structures, then they will be easier to dry. And that's what we realize. Like if you look at here, those thinner walls, they do not show any drying defects, but as we go through that infill structure, we start to see those drying defects again. I also mentioned that air entrapment defects, and we solve that by adding another additive. We remove all the pores during that sample preparation, and then once we have those suspensions, while adding those into syringes, we also realize that we make another air bubbles, and then we degas them to remove all of those defects. And eventually, once those parts are sintered, so these are just the results of the theoretical, the relative densities of the samples that we produce. With those like optimum, the modified formulation, we could reduce the scattering in that density values, and then we could increase the relative densities of that sample. But there were a lot of additives, like dispersant, bubble remover, binder, blah, blah. So we changed the binder, but unfortunately I cannot disclose the its name right now. But by changing the binder and remove all the like bubble removers, etc., just simplify the formulation, we solve all of those issues. And the samples that we obtained had a relative density like up to 99.5%. It was like very high density that can be obtained from that direct ink writing of alumina, and they're all infilled structures. And once we analyze those samples, we realize that the remaining pores are related with the writing pattern during the pattern that we follow during the direct ink writing process. So we still have some room to increase those relative densities by optimizing the additive manufacturing process. So once we compare those like densities with the literature, these are the summary of the all alumina samples produced with direct ink writing. We could achieve very high densities at very standard sintering conditions by using very small amount of additives. And using small amount of additives is critical because it also limits the shrinkage. So here we only had 17.7% shrinkage. That is quite comparable to conventional methods, which is 16.5. So that enhanced the reliability of the components that we produce. So since we have this agglomerate and aggregate-free inks or pastes or suspensions, we were able to get rid of that clogging issues. With that, we could obtain very fine features. So here we just demonstrate microchannels, and you see a printing of two lines next to each other here with the thickness of 0.5 millimeter. So just one line is about like 200 nanometer thickness, which is quite high resolution for direct ink writing under atmospheric conditions. So to conclude, I really hope that I convince you that we really need to go into details. Like we spent time from powder to end product to understand the process, so we can develop simpler recipes that are reproducible and scalable. And I guess the answer is from the simplicity rather than the complexity. With that, this is my current group, and these are the guys working particularly on that ceramic projects. I would like to thank you all for your attention, and if you have any questions, I will be happy to answer. You can hear me, right?
So I see
Okay,
one.
yes.
How to identify the right dispersion to optimize the viscosity.
Excuse me, can you repeat the question again? I couldn't hear.
Yes, it is in chat for a nanoscience.
Lisa, I cannot hear you.
I think it's there's a Q&A question that says, for a nano-sized ceramic powder slurry, how to identify the right dispersant to optimize the viscosity.
Okay, so it wasn't as straightforward like for the ascorbic acid. We actually I knew that the fructose was working, and my initial goal at the beginning to understand how that fructose works and reduce the viscosity of those nanopowder suspensions. But it has like advantages and disadvantages because fructose is like sugary molecule. So if you go like very the suspension they becomes quite sugary sticky, so it was difficult to work with them. So I was looking for other additives to work with them, and we know that the fructose changes the bound water and sodium chloride changes the interaction. So ascorbic acid, if you look at its chemical structure, it has those hydroxyl groups on its chain, but also have this acidic effect. So it reduces the pH and enhance the electrostatic part as well. So I couldn't resolve the whole influence, but I was just screened for like a few additives that are resembles that fructose and the acidic interactions, and then I come up with that ascorbic acid.
Oh, thank you. I think Marcello has his hand up as well.
About the possibility to use different additives in same time, this is also a strategy that is used in the traditional ceramic systems that work very well because it's possible to find synergic interaction between the different additives. And for my suggestion is just to use, for example, approach like a design of experiment that permit to design the best formulation for a mix of the additive, for example, is just a suggestion. Okay.
Yeah, I mean, it's always there. Like, eventually we have to go through that trial and procedures. Like for this ascorbic acid example, I have to screen some of the additives to come up with a good solution. And I'm pretty sure that there are even better dispersants. Like you cannot just tell this is the one. However, like if we can reduce the possibilities as much as possible, that saves time. So definitely, like we have to work with multiple additives, but sometimes we just like go one step back and see if we can simplify that recipe or not. Like that's all I'm trying to say.
Marcello, I would have a question for you since you cited at the beginning of the webinar that you are involved in machine learning approaches and neural network and so on. Do you think that applying machine learning techniques to design of inks, paste, slurries, and so on can be an option? And
Okay,
do
my
you see?
experience was very basic, and I have seen that the very simple neural network permitted fit the data and model a system also with a very few number of data actually. And it is possible also using other techniques. For example, I have used the Monte Carlo approach just to optimize the result. And when I say optimize, don't means only, for example, to have the lower viscosity, the lower yield stress or so on, but a specific viscosity and a specific yield stress, a specific, because sometimes we don't look for the lower viscosity, but for a certain viscosity. And in this way, it's possible to optimize different parameters that are not only the additives, but also the size distribution and so on, using this method. Today, I think that the large language model can be used also to do that very well. I'm surprised that it's possible to use them also with a very low training, thanks to the complexity probably of this neural network. So for me, I think that is a very important tool that both the researchers but also the people that work in the industry should understand and eventually use.
Thank you. Okay, so I think we are at the end of our session for today, and I would like to thank both Marcello and Simge for their help, their effort in preparing these very interesting webinars, and I hope people who attended found inspiration and help for running their current research. So thanks again, Marcello and Simge, and thanks to all the participants. Thank you.
Bye-bye.
Thank you. Bye. Thank you.
Bye, and thank you, Vicki, from the United States, who organized.
Oh, you're very welcome.
Thank
Thanks,
you.
everyone.
Bye-bye.
Bye.